Hello, this is my Physics 2211 Motion of a Falling Object lab report. The purpose of this lab is to observe the motion of a falling object and to create two computational models that predict this motion. The first model only considers the force of gravity, while the second model also includes the effect of drag, which is proportional to the square of the speed and opposite to the direction of motion. The formula is negative b times the magnitude of v squared times v hat, where v is the proportionality constant. Then I will compare the observed motion with the predicted motions from both models. A brief preview is that the second model will predict the observed motion very accurately, while the first will only accurately predict the motion in the beginning. One of the physics principles used in this lab is gravity, which exerts a force vertically downwards with a magnitude equal to the object's mass times g. Another principle used is drag, which is a force that objects moving through the air experience, which is opposite to the direction of motion. Newton's second law is also used, which states that the net force acting on an object is equal to its change in momentum per change in time. If the mass is constant, solving for the final velocity gives the velocity update formula. The last principle used is the position update formula. This is the diagram of the experiment I carried out. My system consists of a folded piece of paper with a mass of 4.34 grams, while the surroundings include everything else such as the ruler in the background, the air, and the earth. Some of the key assumptions made are that the only forces acting on the paper are its weight and drag, that the paper is falling vertically with no sideways motion, that the initial velocity is exactly 0 meters per second, and that the tracker markings are exactly in the center of the paper. The origin was placed vertically below the paper on the floor, with the positive y direction being upwards. This video is the observed motion of the paper. I then used tracker to measure the paper's position each frame. This is the analysis of the observed motion. The initial time was 0 seconds, with an initial height of 1.19 meters and an initial position of 1.19 meters. The time between frames is 1/30th of a second, which is approximately 0.033 seconds. The total time until the paper hit the ground is 0.667 seconds. This section explains how I programmed the initial conditions into the computational models. For both models, the paper's mass was set to 4.34 grams, which is equivalent to 0.00434 kilograms. The initial height was set to 1.19 meters, which was then used to set the initial position to 1.19. The initial velocity was set to 0. The initial time was also set to 0, and delta t, which is the length of each iteration, was set to 1/30th of a second. Additionally, since the weight is the same in both models, it was set to 0 minus mass times g, 0. In the gravity-only model, the proportionality constant b was set to 0, which means that there is no drag, and in the second model, it was set to 0.0068, which was the best value I could find. The iteration loop runs while the time is less than 0.667 seconds. The first step is to calculate the drag force using the formula from before. The function mag calculates the magnitude of a vector, and norm calculates the normal vector of a vector. Then the net force is calculating by adding drag and weight. Then the velocity update formula is used to calculate the new velocity after the time step. Next, approximating v final equals v average, the new position is calculated using the position update formula. Finally, the clock is advanced by delta t, which is equivalent to 1 frame passing in the video. The graph is a time versus position graph, where the pink dots are the predicted motion from the gravity-only model, the orange are from the drag model, and the purple are the observed position. Some of the purple dots cannot be seen because they lie directly beneath the orange dots. Initially, the three positions are very close because the velocity is almost 0, which means there is very little drag acting on the paper, and thus the three positions will be very similar. But as time passes, the velocity increases and so does the drag force, which explains why the gravity-only model deviates from the other curves. The drag model predicts the observed position very accurately all along, which likely indicates that the drag force experienced is very close to being proportional to the square of the speed. Some sources of errors include camera perspective errors. For instance, the final position was marked as being below the origin despite it being placed on the floor. There are also some slight inaccuracies in tracker markings, and only vertical movement was considered. Lastly, the drag proportionality constant could be biased, as it was chosen so that it best matched the real motion. The first additional question is, what does it mean, and asks about terminal velocity. The computational model that includes drag predicts a terminal velocity of about 2.50 meters per second. This can be seen because the curve changes less and less as it approaches -2.5 meters per second. Because velocity becomes almost constant, the net force, which is equal to weight plus drag, is almost 0. Solving for the magnitude of the terminal velocity gives 2.50 meters per second, which is what the drag model predicts. The other additional question is, what if the object was initially dropped downwards? There are three possible cases. In the first case, it is thrown downward with a speed less than the terminal velocity, and as the graph shows, it approaches terminal velocity like it did before. In the second case, it is thrown downward with its terminal velocity, in which case the velocity remains constant. In the third case, the initial velocity is greater than the terminal velocity. Here the object approaches terminal velocity from the other side. In all three cases, the terminal velocity did not change. This happens because terminal velocity depends on mass, g, and the proportionality constant. It does not depend on the initial velocity.